more than 3,500 faults. Not in a dam, not in an Arctic glacier, not anywhere on Earth, on the Moon. Since the first high-resolution images from the Lunar Reconnaissance Orbiter in 2010, scientists have mapped more than 3,500 structures known as lobate scarps, fault cliffs that form when the Moon's crust literally cracks under its own pressure. And here's the detail that changes everything. Most of them did not appear in photographs taken during the Apollo missions. They emerged afterward. They are growing. The Moon is not stable. It is shrinking. And what happens to an object the size of a moon when it shrinks fast enough to produce more than 3,000 visible scars on its surface is exactly the kind of thing scientists would prefer to study for several more decades before speaking publicly. That window of silence is closing. To understand the scale of what is happening, you need one number: 100 meters. That is how much the Moon's radius has shrunk over the past hundreds of millions of years. According to data collected by NASA's Lunar Reconnaissance Orbiter and confirmed by Smithsonian Institution geologist Thomas Waters, it sounds like little. But 100 meters of radial compression, applied to a sphere 3,474 kilometers in diameter, generates crustal pressure equivalent to slowly bending a steel orange. Something has to give. What gives are the scarps, rock walls up to 90 meters tall that tear across the lunar surface like seams splitting open on a deflating ball. The Lunar Reconnaissance Orbiter has mapped more than 3,500 of these structures scattered across the Moon. Some appear in historical photographs from 1971. Most do not. Most simply were not there. So, either the Moon has shrunk dramatically over the past few decades, or the instruments of the past were too crude to notice. Both options are unsettling. The Moon is dying of cold, slowly, but faster than any scientific model from the 1990s predicted. When the solar system formed, 4.5 billion years ago, the Moon was born from a catastrophic collision. A Mars-sized object struck the primitive Earth, and the ejected material fused into an incandescent ball. The Moon's interior was pure magma. Its initial temperature, in the first few million years, may have reached 500 degrees Celsius. Since then, it has been radiating that heat into space. No atmosphere, no oceans to redistribute temperature, no active magnetic field to retain energy. Just bare rock, losing heat to the absolute vacuum. As the interior cools, it contracts. The crust, already solidified, cannot keep up, so it fractures. Think of an orange drying from the inside. The peel does not shrink at the same rate as the pulp. It crumples. It cracks. It forms grooves. The Moon does the same thing, on a planetary scale, with consequences we have only begun to measure now, because only now do we have instruments sensitive enough to hear what is happening inside. And what the seismometers are hearing is moonquakes, lunar earthquakes, triggered by crustal compression, with epicenters concentrated precisely in regions of active scarps, including the South Pole Aitken Basin, the region where NASA plans to land astronauts in the coming years. Before we continue, and what comes next will completely change what you think about the Artemis missions. If you haven't subscribed to the channel yet, do it now. Not because it's protocol, because the next 3 minutes are the kind of thing you'll want to discuss with someone, and the comments section will be active. Subscribe. Hit the bell. Now, let's go deep. In January 2024, a study published in the Planetary Science Journal, titled Tectonics and Seismicity of the Lunar South Polar Region, co-authored by T.R. Waters and researchers from the University of Maryland, brought something that had not appeared in official press releases with enough prominence. The moonquakes recorded by Apollo 17 in the 1970s were not isolated events. They were symptomatic, and by correlating the data from those seismometers with modern images from the Lunar Reconnaissance Orbiter, scientists confirmed that one of the most intense moonquakes ever recorded, estimated between magnitude 5 and 5.6 on the seismological scale, occurred less than 60 kilometers from one of the most active scarps at the South Pole, magnitude 5, on the Moon. which has no tectonic plates, which has no active volcanoes, which should be, geologically speaking, a dead world. Here is what that means in practical terms. The lunar South Pole region, chosen for the Artemis missions precisely because of the presence of water ice in permanently shadowed craters, is seismically active in a way that none of the engineering models for lunar landing capsules was originally designed to account for. The ice is there, the water is there, but the ground beneath it shakes. The study identifies an active fault scarp in the Gerlach Rim 2 region, a candidate landing zone for Artemis III, located less than 60 kilometers from the South Pole. This scarp formed as a direct result of crustal contraction. Recent, geologically speaking, yesterday, and geologically yesterday, can mean within the last 100 million years, or within the last 10,000. Lunar surface dating data carries a margin of error that, in any other scientific context, would render the conclusions provisional. Here, that margin of error is the most important question. NASA has known about this long enough to have changed its plans. And in part, it has. The Artemis program has suffered delays that the agency attributes to engineering issues, funding, and political logistics. All of that is true. But the technical documents from the Lunar Surface Innovation Consortium, publicly available, yet rarely discussed outside aerospace engineering circles, show that the soil stability requirements for lunar habitat modules were revised at least twice since 2021. In both revisions, the seismic factor was raised. They were not expecting a quiet floor. They were calculating how much shaking a habitat can absorb before compromising pressure seals. This is not a secret. It is in the documents. It is in the minutes of technical meetings. But it is not in the enthusiastic promotional videos showing astronauts planting flags in perfect, motionless regolith. Engineering reality and public relations reality rarely inhabit the same press release. Let me be straightforward for a moment. I do not think NASA is hiding this in any conspiratorial sense. The data is public. The studies are peer-reviewed. Researchers speak openly at conferences. The problem is not secrecy. It is that scientific language is dense enough to function as invisibility. What bothers me is something different. It is the distance between what we know and what we communicate. We know the moon is actively shrinking. We know this produces measurable earthquakes less than 60 kilometers from the planned landing zone. We know we plan to land humans in that region within the coming decades. And the public discourse around all of this still uses the same reassuring language as always. Engineering challenge, calculated risk factor, environment to be managed. Perhaps that is exactly it, a calculable problem that competent engineers will solve. But there is something I find worth acknowledging. Never before in human history have we planned to build permanent infrastructure on a celestial body that is literally fracturing beneath its own feet. That is not a reason not to go, but it is a reason to stop for just a moment and let the weight of that land. The moon will keep shrinking. That is not a prediction, it is physics. The lunar interior is still at approximately 1,000 degrees in the deep mantle. It will continue radiating heat into space for hundreds of millions of years. Every degree lost is additional contraction. Every millimeter of contraction is additional pressure on the crust. Every pressure that exceeds the elastic limit of the rock is a new scarp. There is no way to reheat the moon. There is no way to stop the physics of cooling. There is no engineering solution for a geological process of planetary scale. What exists is adaptation. And this is where the subject stops being about the moon and starts being about us. The generation that will build lunar bases, that will mine ice, process oxygen, print structures in regolith, will do so in an environment that is not static, in an environment that breathes, contracts, shakes, one that has its own geological agenda, completely indifferent to human presence. And one detail the Earth never offered: if something goes wrong, there is no rescue in 15 minutes. Shallow moonquakes, triggered by active crustal compression, can last for hours, something without parallel in terrestrial seismology. These are waves that reverberate continuously through the moon's rigid, dry interior, with no layers of molten rock to absorb them. Hours of trembling, inside a pressurized structure, with no possibility of immediate evacuation. That is what engineers are calculating. That is what the press releases do not say. This is the kind of thing I needed you to know, not to cause panic, but because I believe the public conversation about space exploration deserves the same honesty as the private conversation between the engineers who will design the bolts on the landing modules. The moon is changing. It is shrinking. It is cracking. And we are going there anyway, which, depending on how you see it, is either the most audacious or the most typically human thing we have ever decided to do. Now I want to hear from you. Do you think NASA should be more transparent about the seismic risks of the lunar South Pole? Or is the current level of communication adequate to avoid creating unnecessary public panic? Write in the comments. Seriously, this conversation matters. If you made it this far, you already know this channel does not give you the softened version. Subscribe if you haven't already. The next video goes deep into another place the Earth produced that seems impossible to exist. Until then,